Hello guys, how are you? I'm back with the fourth episode of statistical analysis for thesis writing. Finally, we got to a point where we can check the assumptions, and if they met, then we can run the tests. We will cover the health and environmental examples in this episode, and then we will dedicate an entire episode to the psychology example. So for checking assumptions, sometimes you need to run the actual tests. Now we go ahead and start with the health dataset. Remember, we chose logistic regression method for this research. Let's review the assumptions for logistic regression. The outcome variable should be binary. As you can see, it already is. You either have hypertension or not. Having it is represented by 1 and not having it by 0. The second option is that observations should be independent, which means that patients should be different in the study, which they already are. We have 300 individuals, and the study was done on all of them just one time. The third one is that we should not have multicollinearity. Multicollinearity makes it difficult to estimate the unique contribution of each variable. So that's why it's important to be checked. We already checked that using correlation metrics, but if you want to double check and make sure, go ahead and use VIF function. So first, define the logistic regression model using GLM function. Don't forget to define family as binary to show logistic regression. And VIF means variance inflation factor. VIF of less than 5 is acceptable, and if it's greater than 10 is a serious concern. So run it and see all VIF values are close to 1. Since they are far below the thresholds of 5 or 10, we conclude that multicollinearity is not a concern here at all. Next, the two other assumptions are not having strong influential outliers and having adequate sample size, which we covered them already. Both of them are met. We saw in the previous video that we do not have a problematic outlier for the health dataset, and also the amount of sample size, the number of the patients are quite sufficient. Now, let's take a quick look at the results of the logistic regression that we just fit. I'm going to say that again. In this episode, we only check the assumptions and run the models, as we will do the same in the next episode for the psychology example. But in the episode after that, I guess it would be episode number 6, we will go through fully understanding the outputs. So stay around if you want to see the interpreting part of this series. Here, this model estimates how each predictor influences the probability of the hypertension. You see the p-values, and I think all of them are significant, except for 6, right? Now, let's move on to the environmental example. Run all of them, go down. Remember again, we need to run the model first by fitting it to check some of the assumptions. The output variable here is PM 2.5 concentration to measure air pollution. We chose multiple regression for this example. I told you why in the previous video, so if you didn't watch that video already, go ahead and do it. A video in this playlist that is titled episode 3. Anyway, for multiple regression, multiple assumptions need to be checked. First one is linearity. Linearity assumption says that linear regression assumes a roughly linear relationship between predictors and outcome. A common misunderstanding here is that every predictor must show a perfect straight line relationship with the outcome variable when we create a scatter plot. But in reality, multiple regression works a little bit differently. The assumption is not that all predictors must have a strong linear relationship with the outcome by themselves. Instead, the model assumes that the overall relationship between the predictors and the outcome can be adequately represented by a linear relationship. In this example, we have several predictors such as temperature, humidity, wind speed, rainfall, traffic volume, and monitoring station. Some of these variables may show a clear relationship with PM2.5, while others may appear weak or even random when viewed individually. That does not automatically mean that there is a problem, though. A predictor can still contribute information once the effects of other predictors are taken into account. Because of this, the most important diagnostic is not the individual scatter plots, but the residuals versus fitted values plot from the regression model. Let's see the plot together to fully understand what I mean. We go ahead and fit the model to check this assumption. Now the plot, and you see the residuals versus fitted plot. In this plot, we are looking for random scatter around the horizontal line at 0. If we see a clear curve, wave pattern, or systematic shape, that suggests that the linearity assumption may be violated. But you see here, the residuals appear roughly randomly distributed around 0 with no obvious pattern. So the linearity assumption is satisfied, and the linear regression model is appropriate for this data. Another assumption for linear regression that needs to be met is homoscedasticity. Homoscedasticity means residuals variances are reasonably constant across all fitted values. For a dataset, the spread of the residuals should be roughly the same whether the predicted value is small, medium, or large, in order to be considered the assumption is met. The next assumption is independence of errors. We examine independence of errors using the Durbin-Watson test. If the value is close to 2, then it indicates that residuals are independent. Here, our Durbin-Watson statistic is 2.04 with a non-significant p-value. Therefore, there is no evidence of autocorrelation among residuals. The fourth assumption is checking multicollinearity. We already checked this in the EDA process, but let's double check again. And as I said, this time using VIF values, or as I said, variance inflation factor. So run it. And as you can see, all VIF values are close to 1 and far below the commonly used threshold of 5. Therefore, there is no evidence of problematic multicollinearity. And finally, the last assumption is checking the normality of residuals. Regression doesn't require all the variables to be normally distributed. We only need the residuals to be normal. So to check that, we use histogram, QQ-plot, and Shapiro-Wilk test. First, get the residuals of the model simply by residuals function. Run them. By looking at the histogram, I can say the residuals appear approximately bell-shaped, so it is normal. And for the QQ-plot, we can say that when points closely follow the reference line, it indicates good agreement with normality. And finally, for Shapiro-Wilk test, p-value is greater than 0.05, so we fail to reject the null hypothesis. The null hypothesis here was that residuals are normally distributed. So we fail to reject that, then we conclude that the assumption is met. Now we're done with the assumptions for this example. We also saw the results of fitting the multiple regression model itself. At this stage, I only say that the overall model is highly significant. To interpret the outputs of these two examples and the next one in the upcoming video, check the episode after that, episode 6. I'll upload that as soon as possible, as soon as these two finished. But for now, if you have a question, you're welcome to ask in the comment section below. And as always, thanks for watching. If you like video, please click the like button and subscribe to my channel. I'll see you in the next video.